Okay. Well, I can...
Oh, you can do that? All right. Well, thank you. So now we're transitioning. We've talked this morning about the history and some of the problems and concerns about, you know, what has happened and gotten us to where we are now. Now we're going to also turn to, like, what are we doing? We're doing a lot. We want to hear and get up to speed on all the different things that are being done right now to address these issues. And then we're going to go into talking about some other opportunities and ideas for naturally improving water quality. And then finally, we are really going to talk about, you know, the audience's ideas and ways to stay engaged going forward, because it's just the beginning of a process where we're going to be continuing to explore all of this. So with that, if each panelist wouldn't mind taking a moment to introduce themselves before we begin the presentation. Janet? Just to introduce yourself. And then we'll... Sorry.
Do it again.
Sorry.
Yes. Hi, Janet Stearns. I'm with the South Florida Water Management District. I have actually been working on Everglades restoration projects on the west coast for the South Florida Water Management District since 2001.
Good afternoon. For those who aren't here this morning, I'm once again Roland Ottolini from the Lee County Division of Natural Resources.
I am Cassandra Armstrong with the South Florida Water Management District. I'm the section administrator for what is called the Water Quality Treatment Technology section. It used to be called the STA group, which is stormwater treatment areas, and I've been working on the Hicpochee for about 5 years now.
I'm Phil Flood. I'm with the South Florida Water Management District. I'm the legislative liaison and the regional representative. And I'm going to tell you a little bit about the Lake Hicpochee project that we just recently completed over here on the Equalization River.
I'm Lieutenant Colonel Jennifer Reynolds. I'm the Deputy District Commander for South Florida with the Jacksonville District of the U.S. Army Corps of Engineers. And I actually don't have any of my own slides for these presentations because everybody else already had covered all of the things that really they're the lead for. So the Corps is in support of the activities that are being undertaken by the South Florida Water Management District, but I wanted to definitely be here and am happy to answer any questions that people have about the Corps' activities and the Corps' role as we go through these projects.
Great, thank you so much. Janet, you want to begin?
Good afternoon. I hope y'all enjoyed your lunch. Okay, we'll get right into it. I'm going to go through these slides relatively quickly so I don't slow us down. The Reservoir, which we've talked a lot about already this morning, actually is halfway between Moorhaven and Cape Coral. It is just west of LaBelle, sits just south of State Road 80, it's on the eastern side of the Townsend Canal. The reservoir itself will actually be 6 miles by 3 miles. Yes, I did say miles, not feet. So it will be 6 miles by 3 miles. It is a very large above-ground reservoir. The purposes of the C43 reservoir as authorized is to capture excess basin runoff and releases from Lake Okeechobee. And that will be primarily during wet season unless we have an unusual storm during dry season, in which case we would also capture if we have available storage. The intent is we will grab it and store it when there's excess flows, and then when we get into dry season, we will actually hopefully be able to release water to the degree that it actually improves the timing and quantity of fresh water flow to the Caloosahatchee estuary, the goal being to improve that fresh saline mix so that we actually begin to restore that habitat back to a healthier system. In addition to those two purposes for the reservoir, we also have the purpose of maintaining allocated water supply to the local agricultural areas. That will not utilize reservoir water to do that. We will actually do that via the perimeter canal. We will actually pull water out of the Townsend Canal, put it into the perimeter canal, which will then be the vehicle by which we deliver those permitted agricultural uses. In terms of the background, we started this project when the Comprehensive Everglades Restoration Program was started. When I say we started this project, that means we started the planning for this project. And that would have been in basically 2001 that we started. The project implementation report, which is the planning document that lays out what we're going to do, why we're going to do it, and gives you a good cost estimate, was actually approved in 2010. That was actually done concurrently with the initial design documents that were completed in 2007, 2008 timeframe. We did have to update those designs before we could go to construction because of changes in regulation, not because of anything other than that. The actual project was authorized, not appropriated, but authorized by Congress in 2014, and we signed our project partnership agreement with the Corps of Engineers in 2016. Please take note, we actually started work prior to signing that project partnership agreement, so therefore we started work in 2015. But through the authorization, the entire project is part of the federal project. In terms of the actual components of the project, there's the reservoir itself, which is 10,500 acres. It will hold 170,000 acre-feet of storage. It's got two cells. It has two cells because we put a separator dam into it, so when the wind starts to blow, we don't get a lot of wave run up and actually end up with damage to the dam itself. 19 miles of embankment. That includes perimeter as well as the separator dam. We have 15 miles of perimeter canal, 14 water control structures, 3 pump stations, 2 of which, one, the largest, puts water into the reservoir, 1 fills the perimeter canal, and the third one is a very small one on the east end that actually will deliver agricultural water to the permitted users. There are 3 bridges. We actually are doing improvements to the Townsend Canal. And there are, unlike any of the other SERP projects, this one does actually have authorized recreational features associated with it. So we will be constructing recreational features as a part of the project. That kind of recreation will primarily be hiking, biking, kayaking in the perimeter canal. There will be a boat launch into the reservoir. However, it will only be accessible when there's water in the reservoir. And then there will be information kiosk, and there will be actually shelters along the top of the dam so that in the event you get captured in rainstorm, you have a safe place to go. Project delivery. In order to move this project forward to construction, we broke it down into 4 construction packages and 2 preparatory packages. And now I'm going to go through each one of those individually. So the first one is preload and demolition. The preload and demolition was actually originally issued in 2015. That work was completed in 2017, late summer 2017. The function and purpose of the preload and demolition contract was to, first of all, get rid of all the different sheds and pump stations, et cetera, that were on the site. This is an old agricultural site, so we had a lot of infrastructure that had to be torn down and removed. So we took care of all of that. In addition to that, we built what are known as preload mounds. Why did we need to build the big mounds? We constructed 7 of them. They were actually 56 feet high. Highest spot in Southwest Florida. They're slowly coming down, but it was the highest spot in Southwest Florida. On a clear, cold day, you could see all the way to Marco Island. So it was kind of interesting. But the whole purpose of these mounds is there's a clay layer underneath the reservoir, which is exactly why we chose this site to construct an above ground reservoir. However, clay, unlike sand, holds water, and when you start putting weight on it, it will compress. Well, in order to have it compress where we are constructing structures within the dam itself, we wanted to make sure we compressed it before we started constructing the dam. So we didn't build a dam only to have a structure drop 4, 5, 6 feet below where we actually wanted it to be sitting. So that's the actual intent of the preload, the primary intent of the preload package. The second package was the irrigation pump station. That's the pump station that I mentioned earlier that would pump water into the perimeter canal in order to deliver agricultural supplies that are permitted to adjacent landowners. In addition to that, the perimeter canal serves a couple other purposes. We are actually bisecting what's known as the Roberts Canal. So we are grabbing it up, putting it in the perimeter canal, routing it around the east end of the reservoir, and then putting it back into the Roberts Canal in order to maintain historical flows there. The small pump station is 195 cubic feet per second. It is in the southwest corner of the project along the Townsend Canal. This project was actually, the notice to proceed was in early 2016. This project was just completed in April. So we are making progress on the reservoir. It's just we're doing it in pieces. And that's actually a picture of the completed pump station. This is, I'm sure there's a pointer on here somewhere. This down right here is actually the southwest corner of the reservoir because this sits right at that southwest corner. The third package is actually what we call the inflow pump station. That's our big pump station that will lift water out of the Townsend Canal into the reservoir itself. Why are we using the Townsend Canal? Because the property that we acquired is along the Townsend Canal, which is directly fed by or directly feeds to the Caloosahatchee River. So we're only about I would say not even a mile, maybe a mile up from the river. So the inflow pump station, we let that contract in early 2018 with a notice to proceed in March. It is scheduled for completion in 2022. This is the large pump station is in the northwest corner of the project site. And as you can see, there are multiple pieces and aspects to it. Because we don't want different materials of different kinds ending up in an area where they're not best suited for, we actually have to separate all of the material, hence all of the stockpile points. This is the actual station site itself. And then the intake will be right here into the Townsend Canal, which is here. This is north. So the intake will pull water right out of the Townsend Canal into the reservoir, which will run. The reservoir will, at this point, will run right here. And then this is the north boundary, and this is the west boundary. And this is a more current picture. This was just taken last week, actually. This area, this dark area right in the center, is the portion of the pump station that will be below ground. Our pump stations, when we build pump stations, for those that don't know or have never experienced going into one of our pump stations, you'll see a whole lot of concrete above ground, but there's an equal amount of concrete below ground. So they're very large structures. In addition to building the inflow pump station, we are actually having to do improvements to Townsend Canal. Why are we having to do improvements to Townsend Canal? Because we're going to be pulling a lot more water through the Townsend Canal than currently is pulled through it. We are sharing the Townsend Canal with an agricultural area. So it's critical that we not disrupt their ability to withdraw water as they are legally permitted to do, or to discharge water as they are legally permitted to do. So that's a critical aspect. So in order to ensure that if we ever had to pump at the same time for some reason, which is highly improbable, but it could happen, because remember, they irrigate in dry season, typically. We will be releasing water in dry season. However, we won't have to worry about them getting that water because we will operate such that they aren't pulling water at the same time that we're releasing water. So that is a concern that we will handle operationally. And during wet season, we'll be filling water, and they're most likely to be discharging water at that point. So this is State Road 80. This is the Caloosahatchee River, and this is construction that's just about to finish up in terms of the north portion of the Townsend Canal. This weir structure is currently being demolished, and we are doing reinforcements underneath the State Road 80 bridge because we will be increasing the capacity to the maximum design capacity of that bridge, and we will also be doing considerable riprap, etc., shoring up so that the flows don't create any problems for the bridge itself. I mentioned we had two preparatory contracts as well. Preparatory contracts are for the actual dam construction, they weren't needed for the pump stations. So the preparatory work is actually for, the intent behind it was to clear the site of all the trees, etc. We cleared all of the citrus off, probably in 2009, I believe it was, that we cleared all the citrus off. But in the meantime, all kinds of cabbage palms and small oaks, etc., grew up on site. So we actually had to clear the site again. So in order to make sure that wasn't a responsibility of the contractor that won the dam work. We wanted them to go straight to work doing the dam itself. We went ahead and issued a contract to help clear the site. In addition to site clearing, we had two specific areas there. This area and this area, which actually had to be remediated. There were old agricultural chemicals there in such a concentration that it had to be removed. So that work has been completed as well. This area, we discovered or were told about barrels that were buried there. And of course, you can imagine the panic in our hearts when we heard that there were barrels buried there. We had a contractor go out and assess the barrels, and we were most grateful that it was barrels that were used to import frozen concentrate a couple back in the 80s, I think it was. It may have been early 90s, when there was a particularly bad freeze, and so there's a juice plant just to the north of us, so that they imported concentrate in order to be able to produce juice, and that's where they freed the barrels. So that was quite the relief for us. We did have to get rid of the barrels, though, but at least it was just concentrate. This is what the site looked like before we did the recent site clearing, and this is pretty much what it looks like now. Those are all burn piles. We had to wait to burn because we had a very dry year last year, and we could, like everyone else, we had to wait to get our burn permits. That work is now completed. They completed the work in March of this year. In addition to the site clearing, once we got the site cleared, we decided, it would make a lot of sense for us to go ahead and put in access roads. The only way to access the site was through basically two-rut roads through lots of sugar sand and real prone to get stuck. So we actually had about 16 miles of shell rock road put in that allows the dam contractor to move all of his equipment around and get to the various parts and ends of the site. As I was told at lunch today, we actually do have a posted speed limit because of a wealth of threatened and endangered species on site that we have to be very careful of and manage for. So it actually takes an hour to drive the boundary of the site. So it's a huge site. In addition to putting in the lime rock roads, they did, the contractor did remove some additional that were identified that needed to be removed. And that is actually the comparison of what was there versus what we have there now. And this is actually aquatic, not algae. It's aquatic weeds. Okay, so the big important package is the actual dam construction itself. As I mentioned earlier, it's 170,000 acre-feet of storage for those that can't understand what that is. And trust me, it's taken me a very long time to understand what acre-feet of storage really looks like. It's 55 billion gallons of water. This contract was actually issued back in March, and the notice to proceed, which means the contractor's mobilizing to site, was actually on Monday. And as I mentioned earlier, there's a number of structures in the site as well. So this is kind of just a depiction of red is the actual dam, blue is the perimeter canal, and yellow are all the various structures that have to be included. Oops, wrong way. Roland.
Good afternoon. Thank you very much for giving me the opportunity to talk about a little bit about what Lee County is doing in terms of projects in the Caloosahatchee Basin. As far as their applicability or their scalability to the C43 reservoir water quality component, that remains to be seen, but at least it gives an idea of some of the things that can be done in the basin on a much smaller scale. So we're going to go, you've seen a lot of the water quality impairments, source of pollution, such as what we're looking at most of it today. So I'll briefly go through that. We'll do a little project tour of some of the projects we're done, and that will be a slide on some observations we've made. As you've seen earlier, Caloosahatchee is impaired not only for nitrogen but also fecal coliform. We do have the TMDL and the Basin Management Action Plan, which dictates a lot of the water quality initiatives that we have in Lee County. We also realized that identifying the sources are very important. So we've done some joint work with DEP as well as Harbor Branch to do a lot of on the ground truthing, water quality sampling, groundwater sampling, surface water sampling to try to get more definition of where the problems are coming from. Seen these slides before about nutrients, what their sources are. Obviously, urban runoff carries fertilizers, impervious surfaces themselves do not absorb the natural nutrients in the atmosphere, as well as pet waste. We have septic tank failures. What I mean by that is it could be either the structural failure of the tank itself, or it's not designed or maintained properly in the first place. Agricultural runoff, fertilizers, livestock, and wildlife, even natural conditions. There's nutrients coming off of our natural environment, including wetlands and wildlife. And then wastewater industrial sources are also sources of nutrients and bacteria in our waterway. By and large, those are being addressed through the NPDES permitting, so much of that has been taken care of, but there still are discharges in the Caloosahatchee. Just an overview of the local initiatives. Mentioned before, TMDL program. Lee County, as a stakeholder in the Basin Management Action Plan, has to remove 150,000 pounds of total nitrogen per year. And we recognize removing total nitrogen also, well, as mentioned earlier, it's important to remove phosphorus as well. So these technologies should also remove phosphorus when we will be tracking those. We've met about 50,000 pounds, or 1/3 of our way, for the 150,000 reduction requirement. That's the 23% reduction you heard earlier about the TMDL. The projects we've done represent about a $62 million investment over the last 10 years. Land acquisition is very important to Lee County. That's also another means of treating the water, natural systems. Our Conservation 2020 program, that's our land acquisition program, has purchased nearly 29,000 acres since its inception. And that represents about a $400 million commitment when you add in the management costs for those sites. Then we're also active in source identification and control. Amongst others in Lee County, have adopted a fertilizer. We've also initiated a pet waste campaign. You may have seen this out there, some of the billboards. As we speak now, we're working on some new materials. It probably doesn't involve the swamp monster, but it'll be another campaign out there that will address overuse of fertilizers and also picking up after your pets. This map just shows a map of the land acquisitions Conservation 2020 has done. When you add in other federal, state, and private contributions, we have nearly 91,000 acres of preserves in Lee County. That's about a 21% total land mass in the county. Saw this slide earlier. Again, this was based on nutrient data from 2011 to 2015. The point I'm trying to get across here is that what we have been dealing with in the tidal Caloosahatchee, the TMDL we're dealing with is the western portion of this, the tidal, the 20% in this case, or in the B map, it's about 15%. So we're addressing just a portion of it, the downstream end of it, just to give you an idea. There's still, if we really want to realize, people are looking for results on the ground. We really want to realize results in the estuary. Everyone in the watershed from here to Okeechobee and also north of Lake Okeechobee, because of Kissimmee and Fish Eating Creek, they all contribute to the nutrient loading as well. This is a graphic just shows the distribution of our projects in the county. As expected, they align along the Caloosahatchee, Estero Bay, and some actually treat also water going out to Charlotte Harbor. And just a brief overview of some of the projects, kind of a walking photo tour here. A couple we have completed before, you've probably seen these slides. Powell Creek Preserve, there's a 20-acre filler marsh that we constructed in between two mobile home parks in North Fort Myers. Really of basically cleaning up an area that was many years ago without any stormwater treatment. It goes through a series of treatment marshes and then goes into a canal that on out to the river. It's designed to remove about 1,200 pounds of total nitrogen per year. Again, this is design. Potash Creek Preserve, this is an old mine pit. It's a 307-acre parcel of land. About 3,700 acres contribute to that, mostly agriculture. and that's designed to remove about 6,600 pounds per year of total nitrogen. Now, most of these have DEP grants, excuse me, and they require monitoring, so we have a monitoring database on these, but like many of these things, you need to keep monitoring year after year. The variability you get is all over the place. So you kind of, it's hard to just pick one year or one season and say, hey, this is the performance. So it's important to keep up with the monitoring and so that you can identify what kind of efficiencies you are getting. Victor's Creek, this is a 53-acre project, 760-acre park. You probably recognize this as the mountain bike trails in the Caloosahatchee Creeks Preserve area. We built basically some dry detention and wet retention, and that's designed only to retrieve 8 pounds of total nitrogen per year. It's about a 4,800-acre watershed that contributes to that. Prairie Pines Preserve, this is a large parcel we purchased through the Conservation 2020 program as well. 2,600-acre preserve, mostly mesic and wet flatwoods. It can straddles 2 watersheds, Powell Creek and Daughtry's Creek, kind of their headwaters meet in this parcel of land. And primarily what we've done there is to restore the hydrology in the region, filling in ditches, reducing berms, trying to get the natural flow to moving through there. This is just a recent photograph of us cleaning up some of the southwest corner of the park. We get TMDL credit just by restoration. It doesn't have to be a full-blown bona fide water quality treatment project. It's just restoration in itself. It's going to attenuate water, cleanse the water before it released to these creeks. So we like activities like this because it's a very disturbed parcel of land. We're able to make it somewhat resemblance of what it was historically. This is one under construction right now. This is a construction photo from the other day. Null Grade Stormwater Park, North Fort Myers. It's an existing 77-acre park, about a 720-acre watershed, and it's designed with 1,350 pounds of total nitrogen. Let's see, what was that? Sorry. So the water basically moves into this retention facility first. It goes into dry retention or detention, and then it overflows into this. This is a very disturbed wetland, so we're able to rehydrate this, and then it has an outfall structure that returns it back into to the Bayshore Creek. And a larger scale for us, Bob James Preserve is a 5,600-acre preserve. Babcock is north of here. This is the county. Four Corners County is over this way. It straddles 3 creeks, 3 watersheds, Telegraph Creek, Victor's Creek, and Cypress Creek. Mostly mesic and wet flatwoods, at least 51% of it is. But there's about 1,000 acres of former ag fields and pasture on there that we have some opportunities to do some things in terms of water storage and water treatment. And that design right now is underway. We're doing several feasibility options to see what we want to go with. So that's well underway in terms of feasibility. Then a little smaller scale, much smaller scale, L3. This is a former IDD connection in urban Fort Myers, Lee County. Involves Whiskey Creek. The watershed, as you can see just from the graphics, very heavy light industrial, multifamily, commercial. And what we're doing there is going to put a water control structure. Then we also have the opportunity to add some catch basins that will collect the water, some biofiltration, and try to capture some of the area before it goes into the canal. And that's a joint project that we're doing with the City of Fort Myers. Then more recently, we purchased this Olga Shores parcel, 92 acres just west of I-75. It's across from Devil's Elbow and the Caloosahatchee, if you're familiar with the Caloosahatchee River. This is just actually this is a graphic done by an engineer like me. It's probably not going to look like that when we're all done. But we're basically going to create a treatment marsh in here, and also we're going to provide recreational and other amenities on the property as well. So this is just a concept that we're throwing around a little bit right now. And so some observations that we've made over the years when we've done these projects, and a lot of it highly dependent on location within the watershed. You know, you gotta have to be, you know, there's parcels of land out there, but if you're not close to the conveyance, you need to be, so you have a place, a collection point. Availability of flow and how much it varies. You gotta be able to capture the water. Are you just getting it during peaks? Is there a base flow that you can capture? The existing water quality condition. If it's really clean now, you know, and you're trying to remove, you know, the concentration TN is 1.1, are you going to bring it down to it's 0.8. I mean, it gets to the point where it's very difficult to remove that last little bit of concentration. So the idea is to find polluted areas in your watershed that are the highest. You can capture that, and you're going to realize some much greater benefit. The technology used, you can see what we've done, mostly filter marshes, retention, detention, not a lot of high tech there. We have experimented with some ideas with alum and also UV, but we haven't really grown to the point where we'll actually implement those in larger scale. The age of the system is important. And when we first plant these, you got the initial grow in of the plants. They really like to suck up those nutrients, but you can't just let them sit there and die and decay, and it just puts that biomass back into the system. Requires a decent frequency of maintenance so that there's new crop roots coming up to those nutrients, and also takes up some metals as well. As far as results, a lot of folks, what are you getting? You're designing these facilities, and there's design standards out there. We sample them, and the results vary from year to year and also seasonally. Sometimes you look at it and says, well, this is a sink, this is great, it's removing. Other times you're finding concentrations actually higher coming out of them certain times of the year. So we have to really get into that. And we're not scientists to that degree in our office. I mean, we're practitioners. We're trying to get projects on the ground. And so this is my call at the end here is really, we need more technology out there and advancements in technology. Practitioners like us can put systems in without creating a new research and science project, because it seems like every project we do rolls into that, and you've got to do a lot of detail, a lot of background on it. And it would be really helpful for us if we had some things that were tested maybe in the state level or federal level, that practices that are much easier to implement. You heard earlier about the inorganic, organic forms, and we're dealing with the same thing here locally on our small projects. Thank you.
Well, now you're going to hear a whole lot about inorganic and organic forms of nitrogen. Also, I wanted to really thank Dr. Knight. He really did a great job setting up the context for the project that I'm about to present to you. If you remember one of his slides, it was a diagram where there was field scale cells and test cells and mesocosms. I'm the mesocosm chunk of that diagram, and we are essentially what's called phase one of what was to be a large 20-year project, but as you have heard many times today, money. We are kind of at a pause point at this point. We're not going to scale up just yet. We're hoping that budget comes along, but this is the phase one of the water quality treatment and testing project. And we are going to get into a deep dive into science. I will try to keep it as light and airy as possible, but just put your thinking caps on. So as you probably have heard a million times today, Hicpochee is impaired for total nitrogen by the DEP. What you might not know is that almost 80% of that total nitrogen is in what's called the dissolved nitrogen form, and a lot of that is recalcitrant. And what recalcitrant means is that it is unavailable to the algae that we've been talking about, to the bacteria that are in the system, to plants. So recalcitrant is unavailable. So the majority of the nitrogen that's in the Caloosahatchee River is actually unavailable to biology. We did do a study with FIU earlier on to take a look at what actually the Caloosahatchee's dissolved organic nitrogen component is composed of. And the result from that experiment is that it varies. And it ranged from 61% in the dry season to 0% in the late dry season, and stayed 0 throughout the wet season. So what we wanted to do with our mesocosm was to test the wetland-based strategy to see if we could remove nitrogen from the system, especially the dissolved organic nitrogen, from the C43 canal, also known as Hicpochee River. And we had 3 questions that we wanted to address. What plant community will provide the best treatment performance for TN and DOM? The second question was, what contribution will on-site soils have on nitrogen uptake? Back to Dr. Burkhalter's sediment pump. So what happens is when you put the soil into a system, it then flushes out all of the nutrients in there. And if you're starting soil with a lot of nutrients, well, you're going to get a lot of nutrients coming up into the water column. So we wanted to see what the on-site soils actually looked like in that regard. And then the last thing is we wanted to look at the hydraulic loading rate, how much water and how quickly you run through a system, how does that affect the nutrient removal rate. So for the timeline for the mesocosm study itself, we actually started construction in October of 2015, and that got finished in June of the 16. Then we did a startup phase. That was, we let the plants grow in, come to some state of maturity, the water kind of settled out, the sediment settled back down. That was startup phase, and that was over in December of 2016, and then we started operation. The first phase was batch 1, and what that means is we stopped the flow through the system and we let it sit there. And what that was to do was to calculate what's called C-star, which is an assessment of what is the lowest possible concentration you can get within that water. So no flow from January to June 2017. Then we turned the spigots back on, and that phase ran for a whole year. And then we turned the spigots back off and went into a batch 2 for 6 months. And the point of the second one is to see what the difference was between the new vegetation versus the mature, more fully developed vegetation and soil. There we go. And here are our treatments. For our vegetation, we had 2 treatments. We had an emergent treatment and an SAV treatment. The emergent, somebody was wondering about species of plants. So for emergence, we had cattail, bulrush, and spike rush. And for the SAV treatment, we had southern naiad, cara, and coontail. And for the soil, we had our native soils, but then what we also did was, for a small portion of those, we rinsed those soils with hydrochloric acid and hydrogen peroxide to get rid of any labile nutrients that may have been present in that soil. That way we could test the effect of what the native soil was, that sediment pumping, sediment nutrient pumping. And then for HLR, we had 2 treatments. One was a low, which was 1.5 centimeters per day, and then a high, which is 6.0 centimeters per day, which is about the range that our FTAs south of the lake receive. This is what our site looked like. There were 12 tanks. The treatments were randomly distributed around there. You can see if I can get the little mousey to work. These are our subhead tanks here and here. The head tank is way over here off picture. But these subhead, the water was pumped straight from the Hicpochee River into this head tank, which was then distributed to the subhead tanks, and each of these fed 6 tanks. Essentially how that worked. And then you can see on the ground here what that kind of looks like. What's in the foreground is an SAV tank. So we did a lot of sampling in these tanks. We did water quality sampling. We collected a large suite of nitrogen and phosphorus and chlorophyll parameters. We also did physical parameters. Vegetation, we again did some chemistry work on those, as well as did a biweekly assessment of the percent cover of the individual species within the tanks, and then periodically did a biomass sampling. And then we also monitored the soil periodically, checking to see what the nitrogen storage was in those sediments, and then also some other parameters in there. And we also did a couple of side projects. So this one is the biologically available dissolved organic nitrogen. And what we did is we took samples out of each of the tanks as well as from the source water. We brought them back to the lab. We filtered them. And then we measured the starting dissolved organic nitrogen concentration. We then incubated the samples with a small inoculum bacteria that was found in the water column. Incubated them for 28 days, remeasured for DON, and the difference between the two is what was biologically available. So that's how we calculated our BDON component. And by the way, that study was run at the very end. It started in April of 2018 and ended in December of 2018. So during that period, we actually switched. So we've got 2 samplings in the hydraulic loading phase and 2 samplings in the batch 2 phase. So you'll see some results there. And then lastly, we had University of Maryland do a denitrification study. This is them where they took cores from the took them back up to Maryland and measured the amount of nitrogen gas that was effluxing out of the soil. So we also decided not to introduce some turbation into our tanks by removing the unintended vegetation, and we just let it go. So what we ended up with was a lot of other species. Here's a picture of some of them. We had this nice little vine that grew into one of our tanks, as well as this mysterious grass that we have yet to identify. And then the other tank, you can see some little yellow flowers. And we did that for the SAV tanks too, and we get periphyton. So the tank that's on the left is clear of periphyton, that's just SAV, and the one that's on the right is about 20% cover of periphyton, and that impacts how nitrogen flows through that system because 1, you're shading the plants below, and 2, that periphyton is sucking up nutrients, so you might get a little bit of change there. And lastly, we had some volunteers to help us with our sampling, so we actually had a lot of wildlife come into our tanks. So trying to let us know that our tanks were a healthy system. We found some interesting critters in there. One of the most interesting was our crayfish. He was a big guy. He was about 8 inches long. We never actually found the living creature. He kept shedding. He was growing so fast. This is his carapace. So we created a nice healthy ecosystem for these guys to come and populate. And so now to get into the data. What I'm presenting to you from this point on is all preliminary data. It is subject to change. We're still working on the final report, so take everything with a grain of salt there. And one of the things that we found was we did all those lovely treatments, but we found no treatment effects between all of them. The SAV and the emergent were equivalent in how much nitrogen they removed. The hydraulic loads, there was a little bit of something going on there, but nothing that we could really put a finger on. So these data are all rolled up into one pretty little graph, and this is our head tank or our source water data here, and it's broken into the different fractions of nitrogen. So this big blue bar is dissolved organic nitrogen. This reddish one is particulate nitrogen. Green is ammonia, purple is nitrate. So after you run it through Mesocosm, you lose about 23% of your concentration. Almost all of that is the nitrate. There's just this little tiny line of nitrate left. We get a little bit of reduction in ammonia, a little bit of reduction in particulate nitrogen, and a little bit of reduction in DON. Okay. When you do that on a mass basis, however, the number gets a little prettier. We get 33% removal of the mass of nitrogen we flowed into the tank versus the mass of nitrogen that flowed out of the tank. So it's about 33%. So of that tall graph that you saw, the DON component is about 68% of the source water. Overall, we had that tiny reduction. It was about 4% overall. However, we did a deeper dive into the data, and we were able to find that during the wet season, the concentration reduction in DON actually increased to 14%. Yay, we moved the needle. Okay, so we've got something there to chew on. We're excited about that. However, the reduction only occurred when the concentration was over 1 milligram per liter. So, okay, we're not excited about that aspect. So these are the results of the bioassays that I was working on, and they're separated out by the treatment types as well as the time. And as you can see with the vegetation treatment, the emergence did a little better. The emergence, well, let me back up. This graph shows you the percent of the DON that is biologically available. So what you're seeing is that most of the bioavailability is averaging around 7% of the DON being bioavailable during this experiment. And it did range between 0 and 34%, but you can see the error bars. Those are the long sticks off the top of the graph. Those are error bars. So that gives you an indication of how variable the data was. And what this shows you is that when you look at the treatment, the vegetation treatment, there's a little bit higher in the emergence than the SAV, but statistically they're equivalent. Same for the hydraulic loading rate, all about the same, all about the same. When you go over to the month, you can see that September, you actually get a higher bar of BDON. And what I think that is that, remember I told you that we switched from HLR to batch right here between July and June. Basically what we did is we went from a flow-through system to a no-flow system. We increased the residence time during the warmest time of the year. So what happened is all the bacteria that were in there had plenty of time to munch on that DON and make it bioavailable. So we get a nice little spike in the BDON, and then by December, again, it's the same water, no water has come in or out, it's the same water, the BDON has decreased, most likely through uptake. So I wanted to show you this data in a little bit different way. This is biologically available nitrogen, so it's everything that's in the water that is available for uptake or bacteria use. What we found is that during our April and our July, when we actually had source water coming in, this was what it looked like. It was about 0.4 milligrams per liter of the nitrogen is bioavailable. Then once you run it through the mesocosm, it reduces about 80%. So that's really good news. So that means that 80% of what the algal community in the Caloosahatchee would have had available is now gone. So that's good. Then we shut the water off here. So there's no source water to compare. Basically, what this result was the source water for this bar here. And you can see that BDON spiked up. And then after time, same water, no input or output, in December, the bar is much lower over here. We've reduced both the ammonia, the BDON, and we've actually, a little bit of the nitrate came back in, but not significantly. So that's got to be all uptake by the plants in the soil and everything like that. So we think that residence time has a major impact on how nutrients be able to be broken down in the system. And lastly, don't get overwhelmed. I'm not going to walk you through this graph, but these data, what they tell us, what the bottom line is that denitrification is a major source of permanent nitrogen loss to the system. It was about 19% of the amount of decomposition that was occurring in the tanks. 19% of that was denitrification. All that nitrogen is getting blown off. It's equivalent to 2% per day. So that's pretty significant. So very happy about that result. And so our initial conclusions are that treatment wetlands are actually effective for removing dissolved inorganic nitrogen from the Caloosahatchee River. DON is still up in the air, but we did find that there's a seasonal effect, and that may help us understand how to manage any treatment systems that we develop in the future. That microbial community and treatment wetlands are capable of breaking down the DON that comes in from the Caloosahatchee River. It was the water column of the Caloosahatchee, the bacterial community in that is not able to do that. So the fact that once we run it, it can now, we can now make it bioavailable with the different suite of microbes that exist in the wetland versus the water column. And by making it bioavailable, we can then remove it. And lastly, denitrification is a significant pathway for nitrogen removal, a permanent removal of nitrogen from the system. And that's that. I did want to mention real quickly that this was done by a team of folks, WSI, JTech. They did a fantastic job, and I really appreciate it.
All righty. Well, thank you, Cassandra. Great presentation. Happy to hear all about that water quality treatment and testing. And Janet and Roland, I tell you, it's great to see these incredible projects going on in the watershed. I'm going to tell you about one more that's, for those of y'all that aren't too familiar with it, the Lake Hicpochee Hydrologic Enhancement Project. This is a project that the district just recently completed. In fact, we're in the operational testing of it right now. It's not defined specifically as a water quality treatment project, but we expect to see some water quality improvement benefits as a result of this project. So it's the project is located on the north side of Lake Hicpochee. It consists of a 670-acre flow equalization basin, a very shallow reservoir. It was designed to capture stormwater runoff from the C19 basin, which is largely an agricultural area where you can see a large canal running down through there. The idea is to pull water out of the canal, run it through the FEB. From there, it goes into a spreader canal that was constructed along the north face of Lake Hicpochee. The water then stages up in the spreader canal and then flows into Lake Hicpochee, rehydrating it, providing environmental benefits over there. And so it's, as I mentioned, the project was just recently completed. For those of y'all who aren't too familiar with the location, Lake Hicpochee is probably about 3 or 4 miles west of Lake Okeechobee, just outside of Moorhaven. It's a 6,000 acre, well, it used to be a 6,000 acre lake. Most of y'all are familiar with Hamilton Diston, who came to our area and decided to connect the Caloosahatchee with Lake Okeechobee. When he did, he constructed a canal that went right through Lake Hicpochee, and as a result of this and other practices in the area over there, the water dropped and we have a 6,000 acre marsh over there. The beauty is seeing as it used to be navigable waters, it's owned by the state, and therefore kind of opened the door for us to get out there and kind of do some work out there. So you can also see a large canal, C19 canal. It runs all the way from the north near Nicodemus Slough, all the way down along the project, and it too cuts right through Lake Hicpochee down to the C43 canal, the Caloosahatchee over there. These lands surrounding it are largely agricultural, and that C19 canal is the source of water as well as discharge for all those agricultural lands. So the components of this project is the shallow reservoir. It's a 600-mile flow equalization basin, and so it does not have any vegetation in it, but we're just allowing the native vegetation or what's in there to continue to grow. It has a small pump station. It has 3 electric pumps, 350 CFS pumps located in the northeast corner of the project area. It pulls water out of the C19 canal, fills up the flow equalization basin. It's monitored where the water levels drop, then the pumps kick on and keeps the water levels up at approximately 2 feet in there. From there, the water flows out of a fixed crest weir located at the southeast corner of the property, and from there it goes into about a 1 mile spreader canal that was constructed on the north shore of Lake Hicpochee. So here's a picture of the flow equalization basin while it was being leveled when it's under construction. As I mentioned, it's 670 acres in size. There's 4 miles of perimeter embankments and some small levees. They're about 6 feet high, very, very tiny compared to Janet's great big 18 square mile reservoir. We got this little baby reservoir over here. She's got 35-foot dam on that. We've got about a 6-footer here on this one here. So it has a crest width of about 14 feet, and the water depth is going to be 1.9 feet in there. So all total, it's got about 1,300 acre feet of storage, and then there's also 2 miles of seepage canal around 2 sides of the canal of the reservoir to capture any seepage and prevent it from getting under the adjacent agricultural lands. This is just a picture of the outflow structure. It's, as I mentioned, it's a fixed weir. It's simply a large concrete box. Water stages up in that, spills over the sides of it into the box, and it flows underneath the perimeter embankment there into the spreader canal. You can see here on the right over there of the spreader canal. It's about a mile in length over there. And the water stages up in there at a certain elevation. And spreader canal is just a large canal. It's capped on either end. And it's designed where the water stages up in there, and then when it reaches the certain elevation, it spills over the southern end of that. So the water will just flow right over the southern edge of the canal onto Lake Hicpochee, and then make its way sheet flowing down into the Caloosahatchee, or the C43 canals. Here's what it looks like completed, and this is actually while we're in the process of testing it. This is the east corner looking towards the west at the inflow structure. As I mentioned, that's three small pumps in there. Then there's two other smaller pumps that will pull water out of the spread, or the perimeter canal that's located there to the right, in the event that it gets too high. And then down at the southern end over there, you're just kind of looking at the southwest corner, looking towards the northeast, down where the outflow structure is and where the spreader canal is. You can see it's probably about half full right here at this point. It's got maybe a little over a foot of water in it. I was out there about 3 weeks ago, and it's already filling up with lots of birds and a lot of wildlife out there. I will mention that this project will be open to the public for recreational purposes. We have a small boat ramp at the north end of the project where you can put kayaks in. I don't think you'll be able to put any boats in there with only 1.5 feet or 2 feet of water in there, but you'll be able to bike and hike along the perimeter over there, and it should be some outstanding birding, I would think. So. I don't have my slide here, but water quality monitoring, part of the project. This is not, as I mentioned, is not a water quality project, but we are going to be doing some monitoring of the area. Monthly, we'll be recording the water flow coming in there. We've got 2 stations set up. One is on the upstream side of the structure, the pump station at the northeast corner, and then one is just at the outflow. Upstream of the outflow down before it leaves over there. So we'll be monitoring total nitrogen, total phosphorus, dissolved oxygen, and a couple other things over here. And all the data will be posted out there on DB Hydro for folks to see. And as if this project is not great on its own, there's more good news. We've acquired another 2,500 acres of land immediately adjacent to it. It has the potential of providing an additional 9,000 acre storage as well. We would get some funding to move forward with the future design, a feasibility of what's the most appropriate use of these lands, and then incorporate it into the project. The structures that were constructed, the pump station and the outflow and the spreader canal, were specifically designed in mind to accommodate additional flows, and so that won't be a problem over here. So we're looking forward to moving forward in the future of expanding this project over here. And that's it.
All right, so now we're going to go to question and answers. And for those of you who have been with us, you already know the drill, but for those of you on the phone who have joined us, please go now to www.menti.com and use the code 143919. And if you wouldn't mind submitting your questions, they will be posted live as they come in through the internet, along with those people who are submitting their questions in the room. And then our presenters will each take down a couple of these, and as time permits, we'll try to answer at least one per or two per presenter until the end of the Q&A session.
Can I start with some of these?
Sure.
I think we may as well get going here.
Sure.
I see somebody's expressed concern that the EAA reservoir might take precedent over the C43 reservoir. And I certainly don't think that that'll be the case. I mean, we're we're on schedule here I mean, we've got awarded a large construction contract on the C-43 reservoir. EAA is in the design phases right now. We still have a couple of years on there before we'll actually be moving forward with the construction there. So the legislature this year appropriated a large amount of money. We'll be able to have a sufficient amount of funds. Our number one priority of those funds will be continuing forward with the C-43 reservoir right now. So I don't see that being much of a problem.
Yep, and I'll just add on the federal side, even under the limited president's budget when it was $63 million, now it's $200 million for FY20. Even under the $63 million budget, our oversight of the C-43 project was fully funded in FY20 and continues to be so under the $200 million as well.
I'll go ahead and grab will the C-43 be lined? It won't be lined like a swimming pool is lined. The bottom actually has the clay layer underneath of it. There will be soil cement along the banks of the interior of the dam structure. That is to actually prevent erosion. It's not necessarily to prevent seepage, although it will assist with that. There is a very significant seepage management system associated with the design and construction of the reservoir. And another question was, will we move water south or could we move water south via the Townsend Canal? No, we cannot. The Townsend Canal actually very quickly enters into privately owned lands, and we can't move water south through the Townsend Canal. It's only it kind of dead ends when it gets down to State Road 82 anyway.
As far as the standard for cost for projects for Lee County, we don't really have necessarily a standard. You go on DEP's website, you'll see cost ranges everywhere from $200 per pound of total nitrogen removed all the way up to $20,000 per pound of total nitrogen removed. One of the things we're using in-house, though, is we've used for a long time is 10 Mile Canal. When we built that project, we got it around $600 per pound of total nitrogen removed based on the design, and that was including land costs. So that's relatively cheap. So we've had them all the way up to $1,000, $2,000. So, but we kind of use that as our kind of our internal benchmark, but it can be much more expensive than that.
I only have one question up here, and it's actually more of a policy question, but I will try to address it. And that was scaling up the BOMA project to full scale, and wouldn't that make sense to go ahead and do that? There are still some science questions that need to be addressed, and there's also policy questions that need to be addressed, and I'll leave it at that.
I can quickly answer the Mod Waters project. I know it doesn't have to do with this, but I know people are interested in that. So Mod Waters project, the construction is complete on both that and the 11 South Dade project, and we're currently writing the operations plan, so the combined operations plan, COP. We're currently going through the process of writing how we're going to operate that project. And so that's all good news, and we are working very closely with the public and with the South Florida Water Management District on the COP plan.
I know if there's going to be fishing allowed. We have a recreational use question of whether there's going to be fishing.
Absolutely, yeah. There's not only going to be boat ramps in both cells of the reservoir, there will also be kayak launches in the perimeter canal, and I understand there's even planting some littoral shelves in there. It might actually improve the fishing a little bit out there. So
there are littoral shelves that were specifically designed actually to improve aquatic habitat, which leads to another question about whether there's a habitat or wildlife management plan. There is a long-term monitoring plan, much of which involves how we are managing or going to be impacting threatened and endangered species. So our operations plan, which is primarily when we first fill the reservoir every year, because every year we hope to have it actually go dry on us, because we will have used it to meet estuary needs. Will be an operational plan that specifies which we can fill the reservoir so that critters that have gotten into the reservoir while it's dry have the capacity to get out.
Great. So any final thoughts, or is there one question left that one of you wants to answer? We have time for about one more, and then there's a couple at the bottom here.
There's a question about using water hyacinth. We are aware that it's a ability to remove nutrients. However, it tends to be aggressive in its growth, meaning it'll take over everything, which is not exactly in our management plan. So that's why we've avoided water hyacinth.
All right, well, thank you again. If you can join me in congratulating our presenters here.